We now come to the solving part of our analysis of differential equation systems. We know that if we had a set of individual solutions, we could combine them with linear combination. The question is, how do we know what those solutions are in the first place? Well, we saw earlier that the ideas of eigenvalues and eigenvectors would be relevant because the equations we get match those linear algebra ideas. And here is the upshot of that. If we have a system which is written out as some unknown function's derivative is equal to a matrix times that. So this is a homogeneous case. Then, if we can take that matrix and get n linearly independent eigenvectors, and we'll see what that means in practice, then how can we build our solutions? Well, the way that eigenvectors and eigenvalues work together is they come in pairs. So if you have an eigenvalue, it has a corresponding eigenvector, and what we're going to do is put those together. Eigenvalue, eigenvector. And then we'll do the same again for the next part of the solution. Notice it's times t, same as we had before with our characteristic roots. Value and vector, and so on. Then the coefficient out front, which we know belongs there as part of the general solution. This makes far more sense in practice, so let's take a look at some examples. How are we going to solve the differential equation x prime equals ax when A is this matrix here? What does that involve? Well, we just learned that we have to find the eigenvalues and eigenvectors of A. If we can do that, then we can construct our solutions. So how do we find those? There is a reference sheet on the course website, and there's lots of other help available out in the web. So we'll do the fairly straightforward solution here. If you need more background, ask on the forums or take advantage of those other resources. What is the eigenvalue eigenvector equation? Well, it's this AV equals, we'll use R here to match the earlier syntax, equals RV. And again, this is a matrix A and a scalar R here. So we want to solve that equation for R and V. A is given, and we want R and V. The traditional approach to this is to bring this to the other side. So we have AV minus RV equals 0. And what we'd like to do is gather terms, and the way we can do that is A minus R times V equals 0. We're allowed to do that, but we hit a little complication here with the R in the matrix. So to make this a matrix on the R term, we're going to multiply it by I, which is the identity matrix. That's what it's called. And what it is simply ones down the diagonal and 0 everywhere else. All zeros otherwise. And what that does is it's kind of like the one multiplier for regular numbers. It doesn't change or scale things, and it only affects each variable individually. And it turns out it's exactly what we need to solve this equation. The theory we're going to pull out from linear algebra here, even if you don't have it at your fingertips, is that if we have something equals 0, there's two ways that can happen. Either V could equal 0, but that's boring, not too interesting, or this term here could have a determinant that's 0. Doesn't have to be 0 exactly, but it has to have a 0 determinant. So these are the two cases, and this is the one we're interested in, and this is where we go to finding the eigenvalues. What we do is we solve the determinant of A minus Ri equals 0 for R. Let's see how that plays out. So we've got a determinant of A minus Ri, and that's the determinant of A, which is 2 minus 3, 1 minus 2 as a matrix, minus R times 1, 0, 0, 1. And that is equal to the determinant of Notice we can bring this r inside. So we'll leave it, cancel it there, and bring it inside. So what we get is 2 minus r in the top left corner, 2 minus r. The negative 3 is minus 0, so it stays the same. The 1 is minus 0, it stays the same. And then the negative 2 minus r ends up here. We don't usually go through all these steps to get to here, because the upshot is, if you look at the pattern, this is a minus ri is equal to a minus r's on the diagonal. Because the identity matrix is only 1 on the diagonals, we end up with a minus r minus r minus r down the diagonal. Our next phase is to look at our determinant of this 2 by 2 matrix. And 2 by 2 matrices have a nice product rule diagonal element calculation to them. We take this diagonal and multiply it, and then we multiply this diagonal and subtract it. So this is literally equal to 2 minus r times negative 2 minus r minus 1 times negative 3. Again, check out the reference sheet if you're not familiar with determinants. Expanding these terms, we get negative 4 plus 2r minus 2r plus r squared plus 3, or r squared minus 1. And remember, we need this to find an eigenvalue or eigenvector. We need the determinant of this matrix to be 0. And so now we can solve for r. We have r squared equals 1, and so r equals plus 1 or minus 1. And these are the two eigenvalues of the matrix A. And as another notation, this whole thing on the left-hand side here is going to, you had the same name we've used before. It's called the characteristic equation of A. And again, you should notice some familiar territory. Hey, we're going to do some calculations and we're going to end up with a polynomial. It's a second order system, so it's a quadratic. So there's 2 roots, so we can work with those 2 roots to build 2 solutions. Oh wait, this sounds an awful lot like what we've done before. So that's not an illusion, it's actually an underlying structure to all of this, so keep that in mind as you go forward. It's less unfamiliar than it might seem at the first glance. Having found our 2 eigenvalues, what we need to do is find the corresponding eigenvectors next. So for each of these values, there are going to be a single vector that matches it. We'll do this on the next page. Having found an eigenvalue, what we return to is our earlier form of the equation, where a minus r times I times v was equal to 0. And what we're going to look for now is find v given r. So we start with the r value and then we solve for v. In particular, let's start with r equals 1. And so a minus r times I times v is going to equal 2 minus 1. So we take our matrix here and subtract r down the diagonals. Negative 3, 1, negative 2 minus 1 times v. And that's going to equal 1, negative 3, and 1, negative 3. And let's write our vector here as v1, v2. And remember, this is good. Usually with linear systems, having repeated rows is bad, but here it's exactly what we want. This is good because the determinant equals 0, or because one row reduces to all zeros. If we did, now we have to have this equal to 0 vector. Actually, I should add that here for explicitness. This is a vector on the left. It should equal a vector of zeros on the right. The fact that this equation here in the second row is basically redundant means we can just focus on this first issue here, and it tells us that if we expand it out, v1 minus 3v2 equals 0. That's our first row there, expanded. 1 times v1, negative 3 times v2. Another way to write that is v1 equals 3v2 And an important note here is that any multiple of an eigenvector is still an eigenvector, is also an eigenvector. You're not going to get a unique answer to this. And the reason for that is, if you look back at this equation, I could multiply this by 5, and it wouldn't change the right-hand side. I could multiply by minus 10. Again, it wouldn't change anything. So it's no surprise that we have some redundancy or some freedom to choose here. But it means you have to make a choice. So what we're going to do here is let v2 be 1. Pick a nice simple value. If we let v2 be 1, then v1 is going to equal 3 times 1, or just 3. So we're going to get a nice integer vector out of this, which is handy. And so our vector is going to equal v1, which is 3, v2, which is 1, is the eigenvector corresponding to r equals 1. So what we found now is a vector and value pair that lets us build one of our solutions. On the next page, we'll more efficiently move through the second eigenvalue case, which is r equals -1. So for the r equals -1 case, we're going to solve 2 minus minus 1 minus 3. So we're looking at this matrix here, 1 minus 2 minus minus 1. So putting negative r down the diagonals, that times v1, v2 equals 0, 0. Or 2, that's 3, minus 3, this is 1, and -1. And again, we see that degeneracy where this row here is just a multiple of the first row, so we don't really need this for the moment. I guess we could cross off the first line because it's actually more complicated. And we could say from the second row here that v1, so 1 times v1 minus v2 has to equal 0. So v1 has to equal v2. Take your choice of value. Let's let v1 equal 1. And then v2 will also equal 1 because of this. So v2 is going to be 1, 1. Is the eigenvector corresponding to r equals -1. Let's call it r2. And as soon as we have all that information, we're ready to write out our general solution. X of t is equal to c1. r1 was 1 times t times the eigenvector that went with that, which was 3, 1. And then c2 e to the -1 times t times this eigenvector 1, 1. So always e to the r1t times v1, e to the r2t with its matching eigenvector v2. That's how we build our general solutions. As a last step, I think it makes sense to check that what we found actually is correct. We've been taking a lot on faith here. We'll just test each solution individually because that's a little simpler to work through. Again, here's our differential equation up here. The left-hand side is this part. The right-hand side is here. So the left-hand side is just the derivative of this. We can jump straight to that. It's just e to the t times 3, 1. E to the t's derivative is just itself. The right-hand side is our 2, -3, 1, -2 times e to the t times 3, 1. So it's a times x. And that is e to the t times 2 times 3 is 6, minus 3 is 3. 1 times 3 minus 2 is 1. Ah, absolutely. These are equal. Check. Next, for the other solution that we found, the derivative of this would be -e to the -t times 1, 1. So looking at the left-hand side is the derivative of what we started with. The right-hand side, we have to multiply out. There's no real shortcut for that. And we put in our x2 multiplying, so it's a times our solution. And there we get e to the -t times 2 minus 3, which is minus 1, and 1 minus 2, which is minus 1. And we can factor out those negative signs and get exactly the same solution we got up here, negative e to the negative t, 1, 1. So again, that is also a solution. And we have faith in the theory that says if we combine these, we'll get the general solution overall. So that is a start to finish solving a first order linear system